Good afternoon, everyone. I'm Sojin, a PhD student from Korea University. It is an honor to present here at ECCV. Today, I will introduce a novel methodology that addresses noise inverse problems through diffusion trial-based amortized variational inference. In this work, we aim to improve efficiency and accuracy in solving these complex problems across science and engineering. In an inverse problem, we start by defining the whole model y equals hx0. Here, when a clean signal passes through the whole model, we observe a degradation y. However, recovering this underlying signal is not straightforward. This manifold mapping makes the inverse problem challenging to solve. We illustrate the fourth model for the noise inverse problem. Starting with the cleanliness x0, we apply a degradation matrix H, resulting in hx0. We then add an additive Gaussian noise n. Finally, we obtain a noise measurement y. For evaluation, we compare the restored image x0 hat to the ground truth image x0. Let's compare DAVI with previous method. The top shows lead diff and the bottom shows our method DAVI. While lead diff generates only one image, DAVI generates 1,000 images in the same time. In other words, DAVI achieves 1,000 times faster inference speed. This graph shows inference speed. The left axis shows the neural function evaluations, and the right axis shows the time to generate one image. DAVI requires only 20 to 1,000 times fewer steps than baselines due to its one-step sampling. In fact, DAVI generates an image in just 0.04 seconds, about 1,000 times faster than lead diff. We compare qualitative results. DAVI, highlighted in the yellow box, closely matches the ground truth. In contrast, other methods show blurriness and artifacts. This shows that DAVI is not only fast but also preserves high fidelity and immutable details, making it a reliable solution. DAVI and previous methods are compared from two perspectives: inference and optimization. Existing methods use iterative sampling along the reverse diffusion process. They rely on a pre-trained diffusion model. In contrast, DAVI performs a single-step sampling that uses parameterized implicit distribution. For the optimization, previous methods require measurement-wise optimization, which means that they need test time optimization for each sample. In contrast, DAVI trains the neural network using amortized optimization. As a result, DAVI requires no additional test time optimization. Let me introduce our framework, DAVI. To solve the inverse problem, we need to estimate the true posterior Px0 given y. We introduce an implicit distribution parameterized by a neural network to approximate this true posterior using variational optimization. Let me expand the K divergence and drop the constant term. The data consistency term ensures that our generative sample aligns with the given measurement. We can calculate it analytically using the third model equation. The second is the K divergence between the implicit posterior and the clean image distribution. We approximate the clean image prior using a pre-trained diffusion model. Now we aim to optimize the implicit distribution to align with the diffusion prior. However, we face the disjoint support problem. Because the diffusion model has never seen a noise measurement during training, the two distributions do not overlap, making the KL divergence almost infinite. To alleviate the disjoint support problem, we apply the diffusion forward process to smooth the two distributions. We interpret the IKL loss as the KL divergence between two sets of smoothed distributions. We describe how to run the implicit distribution using the IKL loss. First, derive the gradient of IKL with respect to phi, which is the parameters of the implicit distribution. This requires score estimation for both P and Q. However, a corresponding score function for the implicit distribution is not trackable. We illustrate the score distillation gradient to define an implicit score function. First, we reuse the diffusion forward process to smooth both P and Q. For the clean energy distribution P, we adopt a pre-trained diffusion model as a score function. For the implicit distribution Q, we introduce an implicit score function as psi to compute the score for the implicit posterior sample at any time step. This score match function is trained with the denoising score matching loss. As optimization progresses, the score of the implicit distribution evolves. Therefore, we alternate optimization between the implicit distribution and its score function. Furthermore, to improve the robustness to diverse noise measurement, we introduce the perturbed posterior bit, or PPB for short. PPB acts as an intermediate set of trajectories between y and x. Moreover, we introduce a perturbation schedule for noise measurements. We then input the intermediate point YA into the neural network to estimate the clean image. This approach allows us to optimize the implicit distribution with more diverse samples drawn from PPB. We observe that it effectively improves the generalization ability to unseen measurements, including out-of-distribution data. For the out-of-distribution experiment, we set a test dataset different from the training dataset. PyGDM, highlighted in the purple box, shows a hallucination resembling ghost-like artifacts. These examples confirm DAVI's strong generalization ability to unseen distributions. We demonstrate DAVI's versatility through 5 restoration tests. In the top row, our results reveal the microphone with the most detail when zoomed in. In the middle, we restore the please spelling on the cushion. In the left, while the baseline methods show hallucinations, we accurately restore the original barbershop structure. In conclusion, DAVI efficiently performs one-step posterior sampling without the need for optimization at test time. Thank you for having my presentation, and our poster session will begin at 4:30 p.m. I would love to continue the discussion and answer any questions you may have in person. Thank you all for your attention.